us today is the area between two curves. Now we've actually been finding the area between curves. The curves have been the function in y equals 0. So the only difference is now the lower curve won't be y equals 0 anymore. It'll be a different function. So I've got a whole bunch of examples here to show you how it's done. The first one is this problem. It says find the area of the region bounded above by y equals x and below by y equals x, and bounded on the sides by x equals 0 and x equals 1. So the very first thing we need to do is draw a picture. And y equals x is a function, an exponential function that passes through the point 0, 1, and looks something like that, if you recall from pre-cal. And so this is y equals e to the x. And then the second function is y equals x, which is just the line y equals x, easily drawn. And then they give us two bounded bys, and they're x equals and x equals. So they're values of x, so they are vertical lines. So we're going to be bounded by two lines here. And I'm spreading this out just so that we can see it. So the vertical lines are going to be x equals 0 and x equals 1. Now, a lot of times what's difficult about these problems is actually seeing or trying to figure out which area it is that you're trying to find between the two curves. Well, this says bounded above by e to the x and below by y to the x. So this, or y equals x. So it's definitely this area right here. And then we have to make a decision as to whether we're integrating with respect to y or with respect to x. Now, what does that mean? That means my triangles are either going to go with respect to y this direction or up and down. And to me, I hope it looks pretty clear to you that we're going to integrate this problem with respect to x, because the rectangles that we add up have an upper and a lower here like that. So I always draw that little rectangle to help me get oriented as to which variable I'm going to integrate with respect to. All right, so the area between these two curves is going to be the integral from 0 to 1 of the upper curve, which is e to the x, minus the lower curve, x, dx. And the reason the area between those two curves is e to the x minus x is because this distance here from e to the x to the y equals 0, that's e to the x. And then this distance here from here to here is equal to x. And I need the distance in the middle. Well, that's going to be the e to the x function minus this piece here, which is the y equals x piece. So that's why it's upper minus lower. All right, so let's do our integration here. So the derivative, this e to the x is somebody's derivative, and that's e to the x, which we're very happy about, minus x squared over 2 using the reverse power rule, evaluated between 0 and 1. And we can plug 1 in, and we get e to the first minus 1/2 minus, I'm going to plug 0 in. E to the 0 is 1 minus 0 here, because when I plug 0 into the x squared, it goes away. And so we're going to get e minus, well, that's 1/2 minus 1, which is negative 3/2. So that's e minus 3/2 units squared. And that would be the area between those two curves. All right. Moving right along. The next one. Find the area of the region between enclosed by the parabolas y equals x squared and y equals 2x minus x squared. Well, x squared is a parabola we're very good at drawing. And it passes through the point 1, 1. It looks like this. Oops, I should make it more symmetric looking. All right, and then this one here is a parabola that opens upside down, but I have to find its zeros. So I'm going to we'll factor this, and we'll get x times 2 minus x. So the zeros are at x equals 0 and at 2. So we have a 0 at 0, 0, and an x at 2. And believe it or not, this is a parabola that opens down. If these are the x-intercepts, then this is going to be the vertex, because the vertex is always halfway between. Here we go. And that's going to be this area right here in between. Now we lucked out here that this was 1, 1. But let's say we didn't know that. How would we find the points of intersection? Well, what we'd have to do is set these two functions equal to each other. So let's verify it. So when finding the points of intersection, okay, that's going to require us to say x squared equals 2x minus x squared. And I'm going to bring the x squareds to the right, so they're positive. So that's 2x squared minus 2x equals 0. Factoring out of 2x, I get x minus 1 equals 0. So we get intersection points at x equals 0 and x equal 1. Well, sure enough, here we go. At 0, they intersect, and at 1, they intersect. So we found that out just by drawing the picture, which is nice. All right, so now we're going to do the integral setup, which will be the integral from 0 to 1. And I'm going to integrate with respect to x again, because my little rectangle is going to be a dx. And the upper curve is going to be the one that was upside down, which is the 2x minus x squared, minus the lower curve, which is x squared dx. All right, and then before we integrate, let's make it easier on ourselves and simplify the integrand. So this is going to be 2x minus 2x squared, from 0 to 1 dx. And let's do the reverse power rule here, and we're going to get x squared minus 2x cubed over 3, evaluated between 0 and 1. And so we're going to get 1 minus 2/3. And then when I plug in 0, using the fundamental theorem of calculus, part 2, we get a 0 and it wipes out. So the answer is 1/3 units squared is the area between those two parabolas. All right, let's do another example. Well, sometimes we get the upper and the lower curve switching position, and this is the kind of a classic one here. So we're going to find the area, and it's a nice review of sine and cosine of the region bounded by the curves y equals sine x, y equals cosine x equals 0, and x equals pi over 2. And these two are vertical lines. So they're giving us the limits of integration, which is nice in this case. But so I'm going to put a 0 here, and I'm going to put pi over 2 right here. And now we have to graph sine. Well, sine starts at 0, and then at pi over 2, the sine of pi over 2 is 1. So it's going to do the nice bending sine curve there. And then cosine starts at 1 and then ends at pi over 2. And then we're going to find the area between those two curves and those two lines. So what area are we talking about? Well, it looks like we're talking about this area and this area. Now, I haven't drawn it symmetric, but they're looking pretty symmetric to me. And so I'm probably going to use symmetry. But what's interesting is that I need to know what that point is. Well, what is that point? That point is going to be where the sine and the cosine are equal. So finding the point of intersection. What do? Well, we set our functions equal to each other. We're going to go sine x equals cosine x. And there's only one place in the first quadrant where that happens, and that's at pi over 4. But let's pretend you didn't know that. We could divide by cosine x. Now, why can we divide by cosine x? Well, because cosine is not going to evaporate. It's going to get embedded into the tangent here. And where's the tangent 1? Well, that's at x equals pi over 4. And here we go, pi over 4. And so I think what we're going to do is we're going to remember that this is the cosine function here, this orange one. And the other one is the sine function. And like I said, I'd like to use symmetry here. So using symmetry, let's integrate. We'll say the area is equal to the integral from 0 to pi over 4. And I'm going to multiply this by 2. And it's going to be the upper function, which happens to be the cosine function, minus the lower function, which is sine x dx. All right, so what is the antiderivative of cosine x? Well, that's just sine x minus, well, what's the antiderivative of sine x? Well, that's negative cosine x. So this negative turns into a positive cosine x. And we're going to evaluate that between 0 and pi over 4. So let's plug in the sine of pi over 4. Well, that's just root 2 over 2, plus the cosine of pi over 4, which is root 2 over 2, minus 2 times, what happens when we plug in 0? The sine of 0 is 0, minus, or plus, I'm sorry, the cosine of 0, which is 1. So this is going to be 1/2 root 2 over 2 plus 1/2 root 2 over 2 is just 2 root 2's over 2, which is 1 root 2 over 2, times 2 is 2 root 2 minus 2 units squared, and that would be the area between those two curves. All right, a little bit of a review of trig equation solving and using symmetry and trig graphing all at once. All right, well, this next problem I have set up here, you can see the area I want to find. It's this shaded area here. And I have a function that's x equals y squared minus 2 and x equals e to the y. And we're going to find the area of the shaded region. Well, I suggest to you that we're going to do this one now with respect to y, because I have an upper and a lower, or when we do things with respect to y, we always go, if you turn the page this way, this is the upper and this is the lower. So it's always right minus left, because the bigger x values are on this side than this side. Okay, and we're going to integrate from -1 to 1 because this problem already gave it to us, which is really, really nice. They don't always do that. So let's say what the area is here. The area is equal to the integral from -1 to 1. Well, the upper, or the one on the right, is this curve here, which is x equals e to the y. So this is going to be e to the y minus the curve on the left, which is, and I put this in parentheses so we can distribute that pesky negative, minus 2, y squared minus 2, dy, because we're integrating with respect to y. And this is what y is going from and to, -1 to 1. The antiderivative of e to the y is just nicely e to the y. And this will be minus y cubed over 3. And this will now be a plus 2y. And we'll evaluate that between -1 and 1. And sadly, I can't use symmetry here. It'd be nice, but we can't. So let's evaluate it using the fundamental theorem of calculus part 2. We plug the 1 in and we get e minus 1/3 plus 2 minus e to the -1, which is just 1 over e. And -1 cubed is -1, so that'd be a plus 1/3. And then I plug in -1, I get -2. Let's simplify that. We get e. This is going to be minus 1 over e, because I can subtract that. And then this is going to be minus 2/3, right, because it's -1/3 and a -1/3. And this 2 and this 2 are going to be added, so we're going to get 4. So we're going to get e minus 1 over e plus, well, 4 is 12/3 minus 2/3 is 10/3 units squared. It's a lovely number for an area, but that's how you do it. And then when you're integrating with respect to y, it's always right minus left because the higher x values are on the right and the lower x values are on the left. Oops. Next praxis problem. Here we go. We're going to find the area of the shaded region. And I like to highlight these functions sometimes. This one here is the one that I'm going to call the upper function, or the one on the right, and then this one up here is the one on the left. Now what's interesting is that they haven't given us what these points are. Well, I suspect they're 0 and 3, but we shouldn't trust our graph necessarily. So let's find the points of intersection. Now how do we do that? Well, these equations are both x equal equations. So if they're both equal to x, then they have to be equal to each other. So let's set them equal to each other. And we're going to get y squared minus 4y equals 2y minus y squared. And I'm going to move everything to the left to make them positive. So we're going to get 2y squared minus, you'll have to pardon the noise while I'm recording, but that's part of recording at home. Anyway, 4y minus 2y is negative 6y equals 0. And then we're going to factor out some points here. So let's factor out a 2y. And then we get y minus 3 equals 0. And so we get y equals 0 and y equals 3, which is what we suspected. And we're going to integrate with respect to y again, which means we're going to use the function on the right minus the function on the left. And so the area between these two curves is going to be equal to the integral from 0 to 3, because that's what y is going from and to, of the one on the right, the function on the right, which is this orange one here, or the red one. It's 2y minus y squared minus the one on the left, which is y squared minus 4y with respect to y, so that's dy. All right, so let's simplify the integrand before we start integrating from 0 to 3. That's going to be 2y minus a minus 4y. Well, that's going to be a 6y. And y squared minus 2y squared dy. Antiderivative of 6y is going to be 3y squared minus, and this will be 2y cubed over 3, evaluated between 0 and 3. So let's plug the numbers in using the second fundamental theorem of calculus. And when I plug 3 in, I get 27 minus, let's see, y cubed. That's going to be 27 times 2, which is 54. 54 over, actually, this one of the 3's will cancel. So that'll be 18. That's nice. And when I plug 0 in, I get 0. And then when I subtract 27 and 18, I get 9 units squared is the answer, the area between those two curves. Okay? So don't just go by the picture. Double check to make sure you know what the points of intersection are between the two curves. All right? Last one. Sometimes you're given two curves, one of which you know what looks like, and the other one, well, you're not very certain of. Except, let's graph this first one. That's going to be y equals x minus 1. That's easy enough to draw. Y equals x minus 1 is going to be a line with a y-intercept of -1 and a slope of 1, so it's going to pass through these 2 points. There it is, easily drawn. And then the next curve is a little bit trickier, but this is y squared equals 2x plus 6. Well, this is a parabola that opens to the right. Now, how do I know that? Well, because it's y squared. And if we were to solve for x, you'd get y squared equals 2x plus 6. So 2x equals y squared minus 6. X equals 1/2 y squared minus 6. All right, and when I find the point of intersection, I have to figure out where they go. And then if I plug in -3 in this equation up here, I notice right away that y will be 0. So I know that it's going to be a parabola that opens this way. And I don't know where they intersect. I'm not drawing this to scale, but I'm drawing what it looks like anyway. And we're on the hunt to find this area here in between these two curves. Okay, and we're going to integrate with respect to y because the right minus the left looks like it's a one integral setup, which is nice. So we'll integrate with respect to y, and then we have to figure out what these 2 points of intersection are. Okay, and this is going to be x equals y plus 1. So that's what this line is, x equals y plus 1. When we're integrating with respect to y, we have to have our equations solved for x because we're going to have an integrand full of y's. All right, and then this next curve, this parabola is going to be x equals 1/2 y squared minus 6. All right, and now to find the points of intersection. Well, I have solved them both for x, so they're equal to each other now. So I can say that y plus 1 equals 1/2 times y squared minus 6. And I'm going to multiply everything by 2 because I don't like a fraction in the way here. So this will be 2y plus 2 equals y squared minus 6. I multiply everything by 2. And I'm going to leave it on this side because the y squared is already positive. So we're going to get 0 equals y squared minus 2y minus 8. And that thing, believe it or not, does indeed factor. And so we're going to get y and 4 and 2, and this has to be plus and this has to be minus. So the y's are -2 and 4. So we know this point right here is at y equals 4, and this one here is at y equals -2. So what's our integral going to be? Well, our area is going to be the integral from -2 to 4, because we're integrating with respect to y, of the right function, which is going to be y plus 1, minus the left function, which is the parabola, which will be, I'm going to say y squared over 2 minus 3. I'm going to distribute that 1/2. I think it's going to make it easier, dy. Okay, now when you integrate this, you're going to get, now let's simplify first. Area equals the integral from -2 to 4 of y. This is going to be plus 1 minus a minus 3, so it's going to be 4. So it'll be y minus y squared over 2 plus 4 dy. I'm running out of space in this paper, so let me hurry up here. I know you all love doing calculus so much. I'm trying to make my videos short. So when you take the antiderivative here, you're going to get y squared over 2 minus y cubed over 6 plus 4y evaluated between -2 and 4. So what happens when we plug those numbers in? We're going to get 4 squared over 2, which is 8, minus, oh goodness, 4 cubed is 64. That'll be 64 over 6 plus 16 minus, let's plug in 2, and then we're going to get, that's going to be this -2. I'm sorry, we're going to plug in that. We're going to get 2 and then a negative 8, so it'll be a plus 8 over 6, and a negative 8. All right, and since I'm running out of space, I'm going to run up here. Okay, and so when we add all of that up, because this is a minus 8, so this is going to be 16 plus 16 is 32. So it's going to be 32, and let's see, 32. I'm going to reduce this. 2 goes into that 32 times. 2 goes into this 3 times. 2 goes into this 4. 2 goes into this 3. So it's going to be 36 thirds. 36 thirds. And that's 12. Right? So negative 32 thirds minus 4 thirds is a negative 36 thirds, which is 12. So this is 32 minus 12, which is 20 units squared. All right. So that one was a tough one because not only was it oriented, the integration with respect to y, we had to find the points of intersection, and we had to go through and make our equations set up as x equals and x equals so that we would have an integral full of y's so that we could integrate with respect to y. And those are my area examples. Have a great rest of your day.